Hi everybody, can you hear me? Perfect. Okay, so I'm gonna give my talk, message in a bottle. So here it goes. Ruby 1.8 is slow because it's interpreted. Surprise! Ruby 1.9 is interpreted too. Thanks. Any questions? Okay, I'm Konstantin. This is my insanely long Twitter handle. You're welcome to follow me. It just seems long. It's actually not too bad. It's Konstantin until here, like my first name, and then Haase. It's my last name. And on GitHub, so you guys probably know GitHub. It's the sticker company. Turns out they also do code hosting. And on their code hosting platform, I'm RKH. You might know me from the last time you did a Google image search for bike shedding and my face popped up. I work for a company / open source project called Travis CI. Who in here has not heard of Travis CI? Okay, so you too. We do continuous integration for open source projects, for nearly 25,000 open source projects now. We also now have service for private projects. If you have them on GitHub, we can run your tests. Just grab me after this talk. We obviously will charge for this service. That is how we try to finance the work on the open source project. And if you're willing to sign up before we go public, then I can give you a sweet coupon. So just talk to me. This is our Berlin-based team, the Stash. One of our sponsors is Agile Animal, and it's also thanks to them that I'm actually able to speak here. They paid for my travels. Otherwise, I would be sitting in rainy Berlin right now, way colder, and having to work on Travis instead of giving some fun talks. When I added that slide, I actually had to use the Google image search for Agile Animal. Stuff like that comes up. Highly recommended. There are many agile animals out there. Okay, so let's get to the talk. I do a lot of chit chat before the talk because when I go up and talk, I get nervous. And so to calm down myself, what I do is I wonder, what would Aaron Patterson do? Okay, so, but this talk is actually about Ruby. Especially about Ruby internals. And what I want to really focus on is some core aspects of all the Ruby implementations that have to do with performance. And bear with me. It might be that some stuff I show on my slides is not obvious right away, or you don't have to understand all the code. I'll show C++ code, C code, bytecode. You don't have to get all of that. It is important that you get like the general picture of what is going on here. So I already said I'm going to talk about different Ruby implementations. Any guesses as to how many Ruby implementations there are? Just scream numbers. 28. 28. Okay. 55. 51. Okay, you guys are good. I gave the talk in Barcelona, and they were going like 5, 8. They're actually, I think it's 59 or something I found, including stuff like Ruby Motion, or Hot Ruby is actually cool. That's a implementation of the Ruby VM in JavaScript. So you compile your Ruby to bytecode and then run it in a browser. It's by Koichi, I think. Koichi Sasada, the guy who's also behind the JRuby VM. I'm going to focus on the two large ones, which are the two or the three large ones, which are the three Ruby implementations that I would personally consider if I'm going to deploy a Rails app. Ruby 1.9, or the coming Ruby 2.0, JRuby, and Rubinius. And what I want to look at is how they make the method dispatch fast, because it turns out when you run Ruby, what you're doing all the time is actually doing a method dispatch. So for MRI, we're going to look at method dispatch and execution in general. For Rubinius, we're going to look at inline caches and JIT. And for JRuby, we're going to look at invoke dynamic. This doesn't mean that only those implementations do those things. Obviously, all the implementations do method dispatch. All the implementations do some sort of caching, et cetera, et cetera. And the code we're going to look at is this nice code example. It's really handy. I hereby release this as public domain. You may use this. And what it does is actually it gives you a default class. It checks if the ultimate answer is 42 or whatever you pass in here. And it accepts both integers and strings. And we're going to look especially at this one line, always under the assumption that 42 is passed in as argument. So one thing you have to know about all those Ruby implementations is they just love bytecode. So let's look at the bytecode for just this statement, value to s. So all the bytecodes, they're actually like encoding the instructions, but you can also write them as the instruction names, kind of the assembler language of the bytecode. So for MRI, this would actually look like this: get value and then send to s with no arguments to it. For Rubinius, it would look like this: push local 0, because it's the first local variable we have. And for JRuby, depending on the JRuby version and the JVM version you're on, it might look something like this, with some parts missing here, there, and over there. And when you look at that, you might feel like I have no idea what I'm doing. Best thing is the shoes. Do you see that? So let's back up a little. And you might already know that, you might not, depending on if you've played with implementing programming languages. In general, a programming language, or in the Ruby case, especially, it works like this. You start with the source code, which is just a text stream that goes through the parser that generates a parse tree. And the parse tree is just a tree in memory, like +1, 1. You might know that from CS if you took it. And then you can interpret that directly, which will basically walk the tree and send out CPU instructions, which is what Ruby 1.8 does, for instance. Or you could generate a bytecode from that and then interpret that bytecode, which basically is a big while loop that get the next byte and then get the see what instruction that is, read off some more bytes if needed, and again execute CPU instructions, which is what 1.9 always does. Or you could take the bytecode and from that bytecode generate machine code, which is basically the same as bytecode, except the part of the system that understands the bytes and reads in more bytes is no longer software, but your CPU. And so that machine code equals CPU instructions. And the general plan, when we are the VM and we have to do this fast, this part down here. So general plan we have is we have to find a method and then we have to execute a method. But we want to do that fast. So how do we speed that up? Well, we can find the method faster and we can execute the method faster. It's as easy as that. Isn't it amazing? There are actually tricks for doing that. For finding faster, we can do inline caches or call-side caches. We can do lookup caches, which is what MRI is doing. We can do inlining. I'll go into that later on. And well, then for executing faster, we can reduce the operations. That's actually a feature that's coming in MRI. So instead of going the loop around 3 times for taking, or 2 times for taking value and then sending to S, where could be an operation that does take value and send S, so to reduce the interpretation overhead. We can do just-in-time compilation, and most importantly, we can speed up search. Faster search equals faster execution most of the time, because you're just going to call another method that's, again, being looked up. OK, let's look at MRI. First of all, the search. One way you can search for a method is by asking for the RB method entry. That's actually a C method that you can call. It's from the public Ruby API. This one will call RB method entry without cache, unless it has cached in the lookup cache what method actually to find. And what I mean by finding a method is I have the object and the name of the method, and I want to find that piece of bytecode that I now have to execute. And in the end, it will end up in search method, which is actually a pretty clean method. And if you want to hack on Ruby, that's a nice method to play with and just see what happens. This is the method. So the argument is the class, which if the object has a singleton class, then the argument will be the singleton class. Otherwise, it will be the proper class. And ID is the identifier, basically the C version of the symbol of the method name. And what it basically will do is it will loop through the inheritance chain, all the the superclass of the class, et cetera, including all the modules, and look up if in the method table of that class there is a method entry, and if the class at some point is null, nil, then we reach the end of the inheritance chain and still haven't found it and return 0. And otherwise, we already found it, so we have it down here and return it. Now, we have to speed that up. We have to run the method. We have to execute it. At some point, you will end up, there are different ways of executing a method once you get hold of it. But at some point, you will end up at an internal method called vmCall0, which takes a ton of arguments, really not important. The general structure is, here has the VM loop. The VM loop is not a while. Instead, it's a switch, which actually at a lot of points has nested switches, which is kind of weird. This method is really, really long, so I cut out a lot of stuff. And what it has all over the place is a goto again, which is basically implementing the loop. And what you see here is if you have an instruction, it will actually VM exec that instruction, which is now a real bytecode instruction. So how does it know what to execute when it sees that instruction? It looks it up in an instruction manual. It's actually a file in there that's called instructions.dev, I think. Same goes for Rubinius, where you have defined, if I see the following instruction, execute the following code. It actually looks like this. If you see an instruction called send, fetch the class, search for the method, again will trigger search, which is why speeding up search will speed up execution, and then execute the method that is being called. OK. Who's still awake? Let's look at Rubinius. The nice thing about Rubinius is you can play with all that from Ruby. You have the same structure you just saw with C exposed as Ruby objects. Every module has a method table, and that method table has buckets, and those buckets contain compiled code. And so you could implement the search for the method in Ruby. Idiomatic, the same code we just saw in search method, would be something like this. You get the object singleton class, and you don't have the method right now, and as long as it's basically the same code with the while. As long as there is a class and we haven't found the method yet, check in the lookup table for the method and continue with the direct superclass. You can't say superclass here because that would skip included modules. And then what that will give you is actually something called compiled code, the compiled code instance, and you can actually play with that. So if you look up ultimate answer in the method table of deep thought and ask it for its method, you can decode the method, which will give you this. You can look at the opcodes, which will give you this, which is basically a representation of the bytes. So those will be as bytes on the bytecode stream, which can also be written to a file and then executed directly from there. And you can check out the literals, which are 2s, 42, and equals equals. Let's take a close look at that. So I just rearranged it. Up here are the literals, there are the locals, there are the bytes. And then if you group the bytes in wherever there's an instruction, then we can actually see what's going on. So the first byte on the stream is 20. Now Rubinius looks up what is 20, what's the opcode 20? And it turns out 20 is push local. And push local takes one argument. So Rubinius is going to read the next byte, and that is 0. So it's actually push local 0, meaning push the first local. So we're going to check what are the locals. Well, our first local is 42, so we're going to push 42 on the stack. Next instruction is send stack to S0, so we actually send to S to whatever is on the stack. And so we pop off what's on the stack and push onto the stack the result of that method call. So it's 42 as a string. Then we push literal number 1, which is the second literal, 42, onto the stack. So 42, 42 is on the stack. Then we do a string dub to whatever we pushed on the stack. This is because there's 42 as string hard-coded in the code. And if someone would modify that with, say, replace, then it would modify it for all subsequent calls unless there would be a dupe happening. So all the Ruby implementations have to do that there. And then here's an opcode that optimizes equals equals for a lot of cases. And it will actually take those, pop those two off the stack and push true onto it. And then 11 is the bytecode for return, which will just pop off the last thing on the stack. Now, since this is a Ruby object, and this is a real Ruby object, not just the whole thing is not just a representation for reflection onto it, that Ruby object is actually used for execution. So you can modify it, and those modifications will take effect. And that is actually what Rubinius is using internally for implementing inline caches. So what you could do now is you could replace in the literal, you could take the compiled method at runtime and, for instance, replace 42 and the literals tuple. It's not an array, it's a tuple, so like a fixed size array, and replace it with 23. And then from there on, only 23 will be the ultimate answer. You can do the same with the bytes. So you could replace, you could add something, just remove the 11, add some bytes that do something else, and then add the 11 again, and then modify the return value that way, for instance. And Rubinius actually uses that internally to implement inline caches. So if we take a look at the bytes that with their representation, we have push local 0, send stack 2s 0 in there, and the 2s is the symbol object. And what Rubinius does, the first time it sees the code in the execution in the VM, it replaces the 2s with an inline cache. And then the next time it will just ask that when it encounters send stack, it will just ask the inline cache for the method to be executed. And the inline cache holds a reference directly to the compiled code, to the bytes of the compiled code. So when an object comes in and it says send 2s on it, to that object, it doesn't actually have to go through the lookup again. It might already have the the code at hand and just say, oh cool, here's the code, just run this. And what it actually has to do is it has to verify that the code it has at hand is the correct code to execute. That's the big issue with late binding. If you would have a statically typed language without late binding, then you could just at compile time decide what code to call somewhere, which is actually what's happening when you compile C code. So it holds a reference to the code to execute, and it does do a type check. So every class gets a type. I'm not sure what they are, but it's basically just an integer. So for array, the type might be 17. And then when the object comes in, it just checks, is that object type 17? And now, if it's not an array or a subclass, or if it has a singleton class, then the type will be something else. And it knows, oh, I don't have the code for this, so I have to do a lookup again. And now, the nice thing about why it's not just checking, is this array, but is this like 17 or whatever, is that when you add a method to array, override a method to array, or remove a method to array, the type of array will change. Because it might actually be that the method you have to execute has changed. And the nice thing about this is that the check can that way actually be reduced to a single CPU instruction. So the overhead compared to doing a full lookup is really, really low. It's really, really cheap. Another cool thing is that it can actually change what it's pointing to. The machine code, called machine code, it's not machine code at that point. It just means that these are instructions. The naming gets a bit confusing sometimes. And they just have been renamed. This used to be compiled method, and this used to be just code or something. Anyway, why would I want to change it? Because when you change it, you can get specialized method. So, as I said, the default thing is I have the cached bytecode. One cool thing is it can keep the code with breakpoints. You know how when you turn on the debugger on MRI, everything gets slow? That's not the case in Rubinius, because it can have all the optimized code and all the methods, except the one you set a breakpoint in. There it uses the debuggable version and then executes that. And if you step through it into another method by just stepping, it will actually take the unoptimized version, so you can go step through step through step. But as soon as you say continue, it will run all the optimized versions again, and there will be no overhead for running with the debugger, which is also why you can, to running Rubinius process, attach over network and start debugging it, which you cannot do on MRI. And you can specialize it for arguments. You can basically inline bytecode or change branching, et cetera, to run faster for certain arguments that come in. And, well, you can also JIT it. So if a method has been called often enough, Rubinius will actually compile it to machine code and then keep a reference to the machine code. The thing is that compiling to machine code is actually expensive, which is why you don't do it all the time. And what the machine code is you're compiling to depends on the whole system state, which is why it also makes no sense to compile to machine code in advance, or not a lot of sense with the way we develop Ruby applications. For compiling to machine code, it uses something called LLVM. Besides having a cool logo, LLVM is really, really useful. So all Rubinius has to do is take the Rubinius bytecode, translate it into what is called LLVM immediate representation. LLVM stands for low-level virtual machine, even though it is not a virtual machine in the sense we, like Rubinius is. So it doesn't actually execute, interpret the immediate representation. Instead, it always compiles it to native code. And it this has two advantages. It can run a ton of optimizations on the intermediate representation. It can inline stuff and do basically all the optimizations in the sense that Rubinius is doing on the bytecode. It can do on the IR. And also, the intermediate representation is independent of your CPU architecture. And LLVM knows all the CPU architectures and knows tricks to optimize for them. So Rubinius doesn't actually have to care about Intel instructions, about ARM instructions, et cetera, et cetera. That's all taken care of by LLVM. OK. Who's still awake? JRuby. I assume you might not want to hear that much about JRuby, or otherwise you would be at the other talk. Anyways, let's still talk about JRuby. So the nice thing about the JRuby talk being at the same time as my talk is Charlie can call bullshit on my slides. Is this? I'm sorry for saying bullshit on television. OK, so when you were following the buzz around JRuby, you might have heard of something called invoke dynamic. Who in here has heard of invoke dynamic? Raise your hand. OK. Who of these that just raised their hand feels comfortable in explaining how invoke dynamic works? OK. Matt. So let's look at the bytecode, or snippets from the bytecode that JRuby generates with or without invoke dynamic. So without invoke dynamic, the bytecode looks something like this. You have the invoke virtual instruction. So invoke virtual is basically the send of, or one of the method sends instruction of Java, of the Java world. There's also invoke static, but since those are virtual methods, we are calling usually invoke virtual is the default send a method to something. So, but JRuby cannot use that with the actual method name, which is 2s in that case. Instead, it needs to implement its own lookup. So what it does is send to the current, so the current object is the current execution, the object on the stack is the current execution context, whatever, something like that. And it just says get call side 1, which is an object that encapsulates the Ruby method lookup. And so that will end up on the stack. Then we'll push some arguments, like the method name, arguments that are given, the thread context onto it. And then it will call on that object with these arguments. And it should be pretty obvious that if now the JVM does optimizations similar to the optimizations Rubinius does, all it optimizes is the get call side 1 and the call, not actually the Ruby method dispatch. So the nice thing is that the JVM 7 gives us invoke dynamic, and there it changes. The first call just goes away, and the second call gets replaced by call to s. And invoke dynamic basically says, instead of doing a Java method lookup, just I'm going to give you some object that's going to take care of all that, trust me. And the I'm going to give you some object, trust me part looks like this. So the first 3 arguments are actually the same arguments as are passed to invoke virtual calls. So those are actually the 3 things we pushed onto the stack. It's the thread context for the current execution. It's the object that we send the method to, and some other context object. feel free to bother Charlie about this. It's actually not that important for understanding what's going on. And the return value is, again, a Ruby object. And then the new thing with invoke dynamic is that you pass a linker into it. And at the end, arguments that will be passed to the method itself. Let's look at the linker. The rest is really not that interesting. The linker does 3 different things. It does a bootstrap, it has a guard, and it has a fallback. And it points to the bytecode of another JVM method. So the first time the invoke dynamic instruction is encountered, JVM will actually call the bootstrap method. And so at the point in the bytecode, the JVM will have a reference to a call site. A call site is, in that case, basically a JVM method. So we'll have a reference to a JVM method. And that's not there in the beginning because the JVM doesn't know where it should come from because the JVM doesn't know the dispatch. So it's going to call the bootstrap for the linker to set everything up. And in the case of JRuby, the bootstrap will internally call the fallback. Because what's usually the case is if the JVM should encounter it again and there's no method that is pointed at, no bytecode, then we'll call the fallback to fetch the bytecode or to do something else. It doesn't actually have to set up the method. But if you don't set up the method, all the optimizations won't happen. So assumingly, it looks up the method, links the method again, calls the bytecode, executed, all is good. Next time it encounters that point again and calls toS, it could just run the bytecode now or optimize on it the way Rubinius does and in other crazy ways too. But it might actually be that it's currently pointing at the wrong bytecode. So what it does is basically the same thing Rubinius does internally. It calls the guard and says, dear guard or dear linker, please check if everything's still okay. And then JRuby, just like Rubinius, again, does a type check. And it says, yep, everything's all right. And if it doesn't say everything's all right, then the reference to the bytecode will be removed and the fallback will be called. And that way, JVM doesn't have to know anything about Ruby dispatch and can still do all the crazy optimizations in there. So update the JVM and JRuby and get a free performance boost. Okay, so to summarize, things we want to do if we implement a Ruby, or if you want to contribute or want to write your own language or just want to see why some code is slow, why some code is fast, why some Ruby implementation is better for some scenarios than another, is reducing CPU instructions, reducing jumps. Like you can now inline code and that will reduce jumps both on the bytecode level and even on the machine code level because CPUs can optimize for subsequent calls, but not that well for actual jump instructions. And at the same time, doing all that, which a C compiler can also do, but without breaking late binding. And we have a few tools at our hand, amongst them caching, inlining, jitting, and the guards. And remember, fast lookup usually equals fast execution. Thanks.